So when you have low boiling or low melting materials, what can happen is that those things can then diffuse away from the burning core, and you'll have a vapor phase reaction outside of the metal droplet, okay? So in the case of fluorinated materials, when you have that, you have a lot of like silicon tetrafluoride as a gas and all these things. And so it'll be, the oxidizer can readily continue to go in and melt the metal. However, if you start having it where the your oxidizer or the thing that is oxidized starts forming a crust, if it's a permeable crust, you'll still keep burning through until the end. However, if it's an impermeable crust, you never burn all of your material. So having those high melting oxides like tungsten oxide and stuff like that makes it very difficult to burn all of your material. So that's why one of the reasons of using these fluorine materials is actually really good, because the outgassing part is low. So on this one right here, what they were doing is trying to use fluorine containing oxidizers. Now, do you want to use fluorine gas as an oxidizer? No, it's horrible to deal with, right? So what they're doing is they're actually using Teflon and Viton, which are fluorinated polymers, as your fluorine source. And then the metal is going to be, the metal fluoride bond should be stronger than the carbon fluoride bond, and therefore it's going to produce carbon black and your fluorinated materials here. And so if we look at our different systems here where we have a propellant, the propellant here uses aluminum metal as the fuel, okay? And then so in the case of when we burn it in oxygen, what happens is you get aluminum oxide, which is is very abrasive and comes out from your system. Well, in this case here, when you use aluminum with Teflon as the oxidizer, instead of an oxygen-based system like ammonium nitrate or something like that, which would be in a different propellant, we can actually look and see that we get the top one is an aluminized it's got a binder, a polybutadiene binder with ammonium nitrate as the oxidizer. When we move down there, we see we get the same flame temperature on it, no matter how much pressure is inserted here. So in that case, what that means is that as the pressure goes up, you still are burning hot, which means that you can use it as propellant because you can still have thrust. Even as you are getting back pressure inside your thrust nozzle, you can still have it burn. Now, if we look at that right here, we also see that the byproduct from this is aluminum trifluoride, which is a gas. Well, in this case right here, it's subliming at this low temperature here under these different pressures here. And then this is the just aluminum and Teflon by itself, what its heat was, and so it's not actually in a propellant type burn grain. And then this is this reaction, the output of this reaction, showing no change over pressure and having very low temperature, very low heat. So what they're seeing in this system is that when you use these Teflon for the oxidizer in the system, it works really well. Okay, so as we look at this, this is a burning of the material. We start with, this is what the pellet looks like, and then they ignite it from the top. With spherical aluminum, we see the large chunks of spheres coming off. With flake aluminum, we see the large even flakes coming off. This is nano aluminum. This is an 80 nanometer aluminum, and see how it's much more evenly dispersed here. And then this is aluminum with 10% Teflon and aluminum with 30% Teflon. Okay, so we're looking at the amount of materials that are coming off and blowing off and where the heat is generated. Notice all of them create, a little bit of force when they do this. They're actually burning in a jet type direction. In this case here, I think going to a nano aluminum and Teflon would have made it even more exciting. In fact, those are the videos I showed you initially. Those were Teflon and nano aluminum and nano silicon.
So which one performed better, the fourth one?
So this one probably burned faster, but these two burned hotter. Okay, and these two burned about as hot as your normal spherical aluminum, but notice it's a much more even burn.
Can you see that impact?
by the,
Yeah,
by the,
like this.
okay. All right, so then how can you do this with nano aluminum and micronized Teflon? Okay, so if you just do a big chunk of Teflon and you have your nano aluminum in there, you need to have some intimate mix. So you can do the micron Teflon, or you can actually mill it because Teflon is soft enough to be milled. So in this case here, they actually brought a pre-milled 200 nanometer Teflon. And what they were able to do is that they were able to get a much more dispersed, intermixed oxidizer and fuel. Here, these have the big pellets and the little teeny aluminum, but huge chunks of PTFE. So you have a much better oxidizer fuel mixture here. So therefore, it should have a faster combustion rate. And when we look at the TEM of this, we see the ones that have the little, some of them have a little grid pattern in here. You can actually see the crystalline aluminum on the inside. It'll have that crystal packing pattern on them. But it's showing that they are fairly well dispersed. I don't see any with aluminum. I think the dark ones might be aluminum and the lighter ones might be Teflon, just because of density. But usually you can see the little fringes in the aluminum powder. Oh, these are Teflon coated bare aluminum. So what they did was to get a better mixture than just mixing the big Teflon with the little aluminum or the big Teflon with the nano aluminum. They actually were trying to coat them directly on top. So you have this intimate involvement of everything. A lot of fluorine already spread all around the system at once. Okay, so let's look at some of the ways that people have done this. And they try to get, again, the bulk of this work is to try to get your oxidizer fuel mixture to be so intimate that your combustion rate goes completely and goes very quickly. So you can do it with Electrospray. So and I know you've seen electrospinning, right? Okay, Electrospray is the exact same thing, but your viscosity is low enough so that it actually sprays out its little pellets. So you can do that there. Radical vapor deposition on the surface. So you're actually catalyzing the polymerization of tetrafluoride onto the surface there. That was a nice way to do that. Wetting, which is kind of pinky, but the co-solvent adsorption, where you actually have mixtures of solvents, and so one is going to be phase separated out of the solvent onto the solid surface. The co-solvent absorption also here. This is an in situ aerosol coating. So it's kind of like the Electrospray coating, but you're just spraying it and it's drying before it hits the ground. And then a chemical sorption. So they basically are using the natural energy of the aluminum surface to do that. And when they were able to do that, they were able to get nice dispersions. Probably a little too much Teflon in some of these right here. Notice they all have aluminum oxide in them, because there's always a little bit of aluminum oxide. We have to account for that. In fact, a nanometer, an 80 nanometer size aluminum particle has only about 80% combustible aluminum. So a lot of them do these macroscopic ones where they have aluminum oxide. Now, they also have a couple other ones. Most of them use the PTFE or vinyl difluoride, but they can also use perfluoroalkyl carboxylic acids. So those are the things they used to do the Teflon coating on pans. They would do the carboxylic acids right here. And so that's a nice way to do it because that self-adheres to the surface. And so it actually will help with the suspension, and that acts as your fluorine source as well. So there's a lot of different ways to incorporate solid fluorine oxidizer into your system where you don't have to worry about the actual reactivity of the fluorine itself. Okay, let's see. All right, so I want to start with this one up here. Okay, so note that this time scale is nanoseconds. At 0 nanoseconds, they're going to hit a sample with a laser to ignite it. Okay, and at 50 nanoseconds, we see two things. See, we see a dark dot right here that's starting to expand, but then we also see this, what looks like a bubble. Okay, that's the pressure wave. That means this is detonated. That's the pressure wave that's coming out from the surface of the material that's actually flying out. So this right here, there's a, not Riley lines, there's a name for these lines. This is your pressure wave extending out after 150 nanoseconds. And notice we're seeing the evolution of our aluminum fluoride materials coming out here. And then our pressure wave is increasing again with more generation of our solids coming off of our system until we get out to 300 nanoseconds. Our pressure wave is almost being hit by our solids here. And then we have a degradation of the pressure wave and we just have our solids come off right here. So the three things that this tells us one is that number one, it's a very fast reaction. It can be initiated with aluminum, with a laser. And because it generated a pressure wave, it is a detonation. It does count as an energetic material. So, and then you can do that same thing with Nano Teflon. I actually know Tim Foley, he's a friend of mine. This is, I think the larger particles are the aluminum, and then this is a fluorinated material here. I don't think we see any of it here, but it's in there. And so what they were able to do is they were able to build this by that spray type method. And oh, Nano Silicon, that's why, or aluminum. Okay. So the reason that they wanted to use the aluminum or the silicon is because if you look at the energy output for the transfer of the fluorine to the silicon or the fluorine to the aluminum, we actually have the silicon wanting to displace, use up 4 equivalents of fluorine. The aluminum uses 3 equivalents of fluorine. But if we look at the stoichiometry here, that means for every 4 aluminums, we have to have 3 Teflons, which gives us 6 equivalents of carbon and only 4 of these, where here, this is a more energy, thermodynamically better reaction. And your silicon tetrafluoride is a gas at room temperature. And so, and that makes it a little, so if you look at, this is the temperature, and see temperature per, that's temperature per with the amount of silicon used. The rest of it is the Vicon right here. So if we look here, there's temperature is on this graph, volume is on this side right here. We see that as we move from just having silicon here, I mean, just having Teflon here, it burns at a certain rate. And then by adding our aluminum, we get to our max here around 28% silicon. And then our gas volume changes as you go down to 100% silicon, because now you have less of the Teflon and you're burning it as silicon dioxide. So of course your temperature goes down and your volume goes down. Okay, so that means that we have a problem if you're burning your silicon in air, you're going to have that formation of silicon dioxide, which changes the mechanism. When it was generating the silicon tetrafluoride, you're in that vapor phase reaction. And when it's in the silicon oxide, you're in that crust phase reaction. Okay. And then what they looked at was the products. And this is a really interesting program. It's a thermodynamic calculation program used by people who do explosives and energetics. It's called Cheetah. And they can predict what products come off at different parts. And so if you look at this one right here, this is carbon. And so as we start with 0 silicon and we move to more and more carbon, more and more silicon, we actually get less carbon out of the system. Okay. In fact, we see a rise of silicon carbide. So it's actually making silicon carbide, which is also another high melting material. So that's not actually highly desirable. But with the other ones, you have a lot of fluorine and the more volatiles. These are the more volatile systems. This one being the silicon trifluoride. This one being the silicon. Now this is the silicon tetrafluoride. This is the silicon trifluoride. So as we get to higher and higher loadings of silicon, we have less and less of the fluorine available to oxidize our materials completely. And so that's why we got to see the rise of the silicon carbide heat, okay, and the diminishing of the other heats here. So you're running out of fluorine to do the oxidation, so it's just going to do the phase change and go to the silicon carbide. Okay. And then if they compare their results to their where they have the amorphous Nano Silicon, which they bought from Aldridge. It's a nice yellow powder. Nano aluminum you can buy. Novacentrics used to be up in Austin. I think they sold off that part of this and stuff. And then the two binders are just small binders. Notice that one of them is in a solution, the SC one there, so they can get really good intimate mixing there. And the other one is a 200 nanometer powder. And when they did their reactions, they were looking for the different melts of the different byproducts to see where the reaction phase is going to be. So if you'll see here, the heat of vaporization or melt of silicon is about the same as its oxide, but it's much lower. Notice this is in Kelvin too. So this is actually below room temperature. So it's in Kelvin. Silicon carbide, very high melting point, no vaporization or heat point. So that's actually a negative because it's right here with the two vaporization decompositions of the other ones. But if you look at aluminum here, it actually melts slower, so it's easier to initiate. But its oxides are the same as the silicon oxide. And the aluminum fluoride is above room temperature as well here. And the aluminum carbonate is even higher. And then Teflon decays around 600 degrees. So what they're showing here from this is that the benefit of having that fluorine and silicon material is you're producing a very volatile compound in your system. And as we showed on the previous one, you can maximize out for your tetrafluoride with the mixture right here. And so your tetrafluoride maxes out somewhere right around just under 20 degrees. So that you can max out, you can see your maximum amount of silicon and how much of the other binder you want to add in the system. And again, if you're Teflon heavy, that's okay because Teflon melts at a lower temperature anyway. Okay, so let's talk about how their best ones, or the ones they're going to use. Because they found out that 20% silicon is about where they want to be, they did a bunch of them. They varied the percent of the fluorinated material, the Teflon. Remember, this is a liquid, so it actually helps as a squishy binder. And then they varied the silicon, and then they varied the aluminum here. And they looked at their pressure waves. So if we look at our pressure waves here, this first one is with silicon. Okay, and so we can see that these were ignited, and so this is time from trigger of the different materials. And so when you don't have a good fuel to oxidizer ratio, it takes a lot of time from trigger. Here you have a nicer onset. This one right here, you get almost complete combustion in that system. And if you compare the rates of aluminum to the silicon right here, the silicon is the one here in the middle. And by using a nichrome wire to do the ignition time, you have time in milliseconds, distance in millimeters. So basically, this is showing you the rate at which the material burns. Okay, so it burns right in between the aluminum by itself, aluminum and Teflon Vicon, and then this is aluminum Vicon Teflon, but set off by a nichrome wire. So sorry, yeah, nichrome wire. Nickel is a better one. So we see a slightly lower slope. So that could be a good thing right here. This is more indicative of a propellant. This is getting really close to something that detonates to close out. So by having that slower burn, you're actually going to be better as a propellant.
What about the third one, sir? That has its gradually decreasing?
The gradual entry, actually, this is bad because it has two slopes, a slow and a fast. That's going to get you starting to burn, then you'll have a whole bunch of it, then it'll all change burn rate, and that's a bad thing in a propellant. You don't want to do that. It's not a bad thing in a warhead, but it's a bad thing in a propellant. You don't want it to change rates. That broken line is a bad thing. Okay. All right. So then what they did was they analyzed it by their different amounts of type, amounts of the metals in there. Then they looked at an optical burn rate, which was done with high-speed camera, and then the optical mass burning rate. So that's also kind of like by looking at the pellet diminish. And then they looked at their peak pressure. And so when we see here, the 24 was about where we were looking at pretty good. And it's about 300 meters per second, 1,000 meters per second, and then it starts dropping off again. So it turns out that 34% actually is the burn. Actually, if you actually do the calculation, the fluorine to silicon mass ratio is really good right there. You have just a little bit of excess fluorine. But if you look at the burn rates of the aluminum here, so with a very little amount here, you saw very little burning. You saw much faster burn rates across the board. But again, this mixture right here in this about somewhere right around 30%, which is these are the two best there, we get the best performance. And again, it's balancing that amount of oxidizer you have available to the amount of metal you have burning. Okay, and so to graph that, so this is the rate of burn as a function of fuel. So this one is the silicon. It has this nice arc on it. This is the aluminum. It has the nice arc on it. So just by looking at this, you'll say, okay, at a particular burn rate here, it looks like the aluminum material burns faster and hotter than the silicon-based material. And you have a maximum you want to use on both of those different materials. Okay. And so what that kind of looks like as they burn, they actually put these pellets on it. They put a high-speed camera on it, and the dark is what they're actually measuring. You're going to measure from where it starts, and then they're measuring how far it goes down over time. And then that right there is all the volatiles that are coming off when they do this. So this is an optical burn. And notice they have this particular one is the 24%, which is the fastest one for silicon. And they have it at 4.4 megapascals. Again, they're doing it at an increased pressure to emulate being inside a rocket tube. And that buildup in pressure inside a rocket tube for its propellant qualities. Okay, so of all the stuff about nanoenergetics is that all metals burn if you get them small enough. Okay, they burn by different mechanisms based on the oxides or the fluorides that come off. So we can change that. The closer the oxidizer is to the fuel, the faster it goes. Nanothermite is detonable. Regular thermite just gives off a lot of energy and a lot of liquid iron. Oxygen is not our only oxidizer. Now, in most propellants here, you have ammonium nitrate or something like that. Oxygen is still the oxidizer. But in the case of the fluorine system or the Teflon and Bipon system, we have fluorine as our oxidizer. Those are actually two of the best oxidizers out there. If you look at where they are in the periodic table, chlorine's okay too, but fluorine's better. As with all nanocomposites, processing is crucial, right? So if you don't process it right, it's not going to do what you want it to do. And in the case of the aluminum side, the smaller the aluminum, the smaller the fluorine source was, whether it was the perfluoroacid or the micronized Teflon or the liquid Teflon, the better results you found. So mixing and processing is critical. And that is all I have on that. And it's 3:01. So, okay. So again, you will, let me stop.